Welcome to the Sleepless Universe. In this video, we will explore the most dangerous places in the cosmos, regions where the laws of physics are pushed to their absolute limits. From the edge of black holes to the heart of exploding stars, each of these locations is more extreme than the last. If you enjoy this kind of content, I would love it if you left a like and subscribe to the channel. And let me know in the comments where you are watching from and what time it is for you. Now, settle in, relax, and enjoy the journey. Event horizons. At the edge of black holes, there are regions in the universe where the very structure of reality bends to the breaking point. One of the most extreme and perilous of these places is the event horizon of a black hole. Unlike the rocky surface of a planet or the bright flames of a star, the event horizon is not a tangible surface you could stand on or even touch. It is an invisible boundary defined entirely by the laws of physics. Cross it, and you are gone from the observable universe. Nothing can escape from within. Not light, not matter, not even information. It is the cosmic equivalent of a one-way door, and on the far side of that door, the rules change forever. To understand why the event horizon is so dangerous, we need to look at how it forms. Black holes are born when massive stars far heavier than our sun, reach the end of their nuclear life. Throughout their lifetimes, these stars burn hydrogen, then helium, and eventually heavier elements in their cores, producing the outward pressure that balances the inward pull of gravity. But when they exhaust their fuel, the balance is lost. Gravity wins. The core collapses under its own weight, crushing atoms, then subatomic particles, into a state so dense and compact that space and time themselves are dramatically curved. The collapse continues until all of the star's mass is concentrated into a point of zero volume, a singularity. Around that singularity, gravity becomes so intense that there is a precise distance at which the escape velocity, the speed needed to break free, equals the speed of light. This is the event horizon. Since nothing can exceed the speed of light, anything crossing that threshold is trapped forever. It does not matter how powerful your engines are, how strong your rockets burn, or how much you fight against it. Once you cross that line, every possible path through space and time leads inward toward the singularity. From far away, a black hole might not look dangerous. Without an accretion disk, that bright, swirling disk of hot gas and dust that often surrounds an actively feeding black hole, it could be completely invisible against the blackness of space. In fact, astronomers have found that many black holes lurk silently, not currently feeding, giving no obvious signs of their presence until something ventures too close. It's this silence that makes them so deadly. A ship or a planet could drift unknowingly into their reach without realizing the danger until it is too late. Imagine you were in a spacecraft approaching a black hole. At first, you would feel almost nothing unusual. The gravitational pull would increase gradually, just like approaching a large planet or star. But the closer you get, the faster you would have to travel to escape. At the event horizon, the required speed becomes the speed of light itself. And since no object with mass can travel at light speed, there is no way to turn back. From your point of view inside the ship, you would cross the horizon without any dramatic flash or explosion. But to an observer watching from a safe distance, you would appear to slow down, your image stretching and reddening due to gravitational redshift, fading until it disappears entirely. This warping of light and time is a direct result of Einstein's theory of general relativity. Near an event horizon, the curvature of space-time is so extreme that time flows at a different rate depending on your location. For someone watching from far away, time seems to stop for you as you approach the boundary. For you, time passes normally, but the outside universe appears to speed up. In theory, if you hover just outside the event horizon, somehow resisting the pull, you could watch the entire future of the universe unfold in minutes or hours. Stars would age, galaxies would collide, and the cosmic clock would race forward at an impossible pace. The danger here is not only that you cannot escape once you cross the horizon. Even before reaching it, the forces at work can be fatal. These are called tidal forces. The differences in gravitational pull between one part of your body and another. Near a small black hole, the difference between the gravity on your feet and on your head could be so extreme that you would be stretched lengthwise and compressed sideways in a process scientists call spaghettification. This name might sound almost humorous, but the reality would be instant and lethal. Your body, your ship, even the very atoms making up your structure could be pulled apart. For supermassive black holes, the kind found at the centers of galaxies, the situation is a little different. Because their event horizons are much larger, the gradient in gravity across your body could be smaller at the point of crossing. You might pass through the horizon without feeling extreme tidal forces immediately. But that only delays the inevitable. The deeper you go, the stronger the forces become, and eventually they would overwhelm you just the same. Event horizons are not just astrophysical curiosities. They are a challenge to our deepest understanding of the universe. One of the great puzzles is the information paradox. According to quantum theory, information about the state of matter cannot be destroyed. But if matter falls into a black hole, it seems to vanish from our universe forever. Where does that information go? Is it preserved somehow on the surface of the event horizon, as in the holographic principle? Or is it truly lost, forcing us to rethink the foundations of physics? And then there is Hawking radiation, a theoretical process proposed by Stephen Hawking in the 1970s. It suggests that quantum effects near the horizon allow black holes to slowly emit radiation, losing mass over incredibly long timescales. For a black hole with the mass of a star, this evaporation process would take many times the current age of the universe, so it doesn't make them any less dangerous for us now. But it does hint that event horizons are not entirely static or eternal. Near an actively feeding black hole, the region outside the event horizon can be as deadly as the horizon itself. The accretion disk can glow hotter than the core of a star, producing intense X-rays and gamma rays. Magnetic fields twist and snap, launching jets of particles at near-light speeds out into space. These jets can extend for hundreds of thousands of light years, cutting through entire galaxies. If one of those jets were pointed directly at Earth, it could strip away our atmosphere in seconds, ending life instantly. The event horizon, then, is not a gentle line drawn in space. It is the ultimate cosmic trap, often surrounded by a maelstrom of violence and energy. And even though we cannot see past it, we know enough to understand that crossing it is the end of any journey. No rescue, no signal, no return. It is one of the universe's most absolute rules. Once you cross the event horizon, there is no turning back. This is not a poetic exaggeration, but a hard, mathematical reality. Inside this invisible boundary, space and time behave in ways that defy our everyday experience. It is not just that space is curved. The very concept of direction changes. Moving forward in time inevitably means moving closer to the singularity. No matter which way you try to steer, every possible path through space-time ends at the same destination, the infinitely dense center of the black hole. This inescapable pull is one reason scientists describe black holes as the ultimate one-way trip. Even light, which travels at the fastest possible speed in the universe, is trapped once it crosses the horizon. If a flashlight beam were aimed outward from inside, the photons would simply spiral inward, unable to gain any ground against the warped space-time. In that sense, the event horizon is not just a place where escape is impossible, it is a place where the very definition of movement changes. Approaching the event horizon is a gradual process from the outside. Gravity grows stronger, time dilates, and space stretches. But the moment of crossing is, paradoxically, ordinary for the person falling in. There is no sudden flash, no wall of energy, no physical marker at all. The laws of physics remain smooth across the boundary. If you were free-falling, you might not even realize you had crossed until it was far too late. The only clue would be that escape had become mathematically impossible. From the perspective of someone far away, however, the story is very different. They would see you slow down as you neared the horizon, your signals taking longer and longer to arrive. The light from you would become redder and dimmer due to gravitational redshift. Eventually, you would appear frozen in place, hovering just above the horizon, fading into darkness. To them, you would never seem to cross it at all, even though, from your own point of view, you would have already plunged inward. These differences between perspectives are one of the most mind-bending aspects of general relativity. They show how reality can look entirely different depending on where you are in the gravitational field. For the person falling in, The journey continues unimpeded. For the outside observer, the fall never finishes. Both perspectives are valid within their own frames of reference. The size of an event horizon depends directly on the mass of the black hole. For a black hole the mass of our sun, the horizon would be only a few kilometers across, about the size of a small city. For a supermassive black hole with millions or billions of solar masses, the horizon could be larger than the orbit of Mercury, stretching for tens of millions of kilometers. In either case, the boundary marks the same fundamental threshold. The escape velocity equals the speed of light. But the environment near the event horizon can differ drastically depending on the black hole's circumstances. A quiet black hole that is not actively feeding may have relatively empty surroundings, with little radiation or matter in its immediate neighborhood. Such an object could be almost impossible to detect, except through its gravitational influence on nearby stars. On the other hand, a black hole with an accretion disk is one of the brightest and most violent phenomena in the universe. The matter in the disk, compressed and heated to extreme temperatures, can shine with more energy than entire galaxies. One of the great scientific achievements of recent years has been the direct imaging of a black hole's shadow. In 2019, the Event Horizon Telescope collaboration released the first image of the supermassive black hole at the center of galaxy M87. The image showed a glowing ring of light surrounding a dark core, the shadow cast by the event horizon as it blocks light from behind. This shadow is not the event horizon itself, but it is the closest visual representation we have ever achieved. It confirmed predictions made by Einstein's theory more than a century ago, and gave us our first real glimpse of this cosmic boundary. Yet, for all we have learned, many mysteries remain. Does the event horizon have a precise, sharp edge, or is it fuzzy due to quantum effects? Is it possible that the horizon could act as a kind of firewall, instantly incinerating anything that falls in? This firewall hypothesis is one proposed solution to the information paradox, but it would require breaking some of the most well-established principles of relativity. No one knows the answer for certain, and testing these ideas is extremely difficult. Speculation also exists about whether an event horizon could be connected to another part of the universe, or even another universe entirely. In theory, certain solutions to Einstein's equations allow for wormholes, tunnels through space-time, to form inside black holes. But these solutions are unstable and would likely collapse before anything could pass through. Even so, the idea persists in science fiction and in some branches of theoretical physics, because the mathematics leaves open the possibility, however remote. From a survival standpoint, there is nothing more important than avoiding an event horizon altogether. In practical terms, that means staying far away from regions of intense gravity. For a spacecraft, this requires careful navigation and constant awareness of the gravitational landscape. Even the smallest miscalculation could mean drifting too close and finding yourself caught in the inescapable pull. Unlike most dangers in space, radiation, collisions, or hostile environments, there is no technology, no amount of shielding, and no amount of fuel that can get you out once you cross that boundary. In the grand scheme of the universe, event horizons are relatively common. Billions of stellar mass black holes are thought to exist in our galaxy alone, along with a supermassive one at the galactic center. Most are harmlessly far away, but the knowledge that such traps exist, waiting silently in the darkness, is a reminder of the universe's indifference to human concerns. The event horizon is, in many ways, the ultimate symbol of danger. It is invisible, silent, and absolute. It cannot be bargained with or overcome. Once you cross it, your fate is sealed. It is this combination of inevitability and mystery that makes it one of the most fascinating and most dangerous of the places in the entire cosmos. Inside the event horizon, all concepts of normal navigation and physics as we understand them collapse. The singularity, the infinitely dense heart of the black hole, lies ahead, not in the sense of ahead as a direction in space, but ahead in time. In other words, the singularity is not a location you can steer away from. It is a moment in your future that you cannot avoid. Every tick of your clock, every beat of your heart, every moment you experience brings you closer to it, no matter what you do. To understand how strange this is, imagine replacing the floor beneath you with a massive conveyor belt that moves toward a furnace. Once you step on, no matter how much you run in the opposite direction, you still get carried forward. On the event horizon side of reality, the conveyor belt is space-time itself, flowing inward faster than you could ever move outward. In fact, from inside the horizon, even light is swept toward the singularity. Not because it slows down, but because the very stage on which it moves is tilting steeply inward. Scientists often describe space-time around a black hole using the analogy of a waterfall. Imagine a river flowing toward the edge of a waterfall. A fish swimming upstream far from the edge can escape easily. Closer to the edge, the current gets stronger. At some point, the event horizon in this analogy, the current moves faster than any fish can swim. Beyond that point, the water itself carries everything over the edge, no matter how fast it tries to swim against the flow. Replace water with space-time and fish with light, and you have a simplified picture of why the event horizon is a one-way boundary. The most extreme physical conditions in the known universe exist inside this invisible line. Density and gravity become so intense near the singularity that our best theories break down. Einstein's general relativity predicts the singularity as a point of infinite density, but infinity in physics is usually a sign that the theory has reached its limits. Quantum mechanics, which governs the smallest scales, must also play a role, but no one yet knows exactly how. A complete theory of quantum gravity, the unification of general relativity and quantum mechanics, is needed to truly describe what happens inside. But we do not yet have it. For now, what happens beyond the event horizon remains forever hidden from the outside world. Signals cannot get out, and so even the most advanced telescopes cannot see inside. This limitation makes black holes and their horizons both scientifically frustrating and deeply intriguing. They are like sealed boxes with windows painted black. You can study the outside in exquisite detail, but the inside remains unknowable. Still, we can study the effects an event horizon has on its surroundings, and these effects can be dramatic. Gas clouds drawn toward the black hole heat up and emit X-rays as they spiral inward. Magnetic fields twist and reconnect, releasing bursts of energy. Entire stars can be shredded in a process known as tidal disruption. Their matter stretched into streams that wrap around the black hole before disappearing inside. Observing these events gives astronomers indirect but powerful evidence of the event horizon's presence. Interestingly, there is no minimum mass for a black hole. In theory, a black hole could be as small as a single atom if enough mass were compressed into that tiny volume. Such micro black holes, if they exist, would have event horizons far smaller than a proton. They would evaporate quickly via Hawking radiation, making them short-lived and harmless. The ones we know for certain exist, stellar mass black holes and supermassive black holes, are much larger, and their event horizons range from a few kilometers to billions of kilometers across. When scientists discuss the danger of an event horizon, they often emphasize its inevitability. Most other cosmic hazards, like supernova explosions or gamma-ray bursts, have a chance of being avoided if you are far enough away. But an event horizon does not care how fast you are, how clever your trajectory is, or what kind of propulsion you have. The danger lies in its very geometry. Once you cross, you are on a one-way path to an unknown and inescapable fate. The philosophical implications are as heavy as the physical ones. The event horizon represents a limit to human knowledge, a reminder that there are regions of the universe from which no information can return. This raises deep questions about determinism, the completeness of physical law, and the ultimate nature of reality. Are there events happening right now inside black holes that will never be part of our observable universe? If so, those events might as well be in another universe entirely, cut off from ours by an unbreakable wall. Some theories suggest that the information about everything that falls in is somehow preserved in a scrambled form on the surface of the event horizon itself. This holographic principle proposes that the three-dimensional reality inside the black hole might be fully encoded on its two-dimensional surface. If true, the universe itself might work like a vast hologram, with all the information about a region stored on its boundaries. While compelling, this idea remains speculative and has not yet been tested in a definitive way. In the end, what makes the event horizon so dangerous is not that it actively destroys things. It is not a wall of fire or a blast of energy, but that it removes them from the universe we know. It is the ultimate eraser, the point beyond which you are no longer part of the cosmic conversation. From the outside, you become invisible. From the inside, you are carried inevitably toward the singularity. And there is no reversing that journey. For explorers, whether human or robotic, the event horizon is the clearest possible do not cross line the universe can draw. And yet, its mystery is exactly what makes it irresistible to scientists. We cannot help but stare into the darkness and wonder what lies beyond. Some scientists have even imagined scenarios in which approaching an event horizon could be used for scientific discovery, though these are purely hypothetical and almost certainly impossible for anything we want to survive. The idea is that you could send a probe toward the horizon, collecting data right up to the moment of crossing. To an outside observer, the probe would appear to slow and fade, but in the moments before it vanished from view, it could transmit unprecedented measurements of the extreme gravitational environment. In reality, however, the immense radiation near active black holes and the danger of spaghettification make such missions impractical. Yet, despite the deadly nature of event horizons, they also play a critical role in shaping the universe. Supermassive black holes at the centers of galaxies influence the formation of stars, regulate the flow of interstellar gas, and can even drive powerful galactic winds that affect regions hundreds of thousands of light years away. In this sense, event horizons are not just destructive. They are part of the cosmic engine that builds and shapes galaxies themselves. Without them, the universe might look very different. Astronomers also use event horizons as natural laboratories for testing the limits of physics. The incredible warping of space-time near a horizon is an ideal environment to test Einstein's general relativity under extreme conditions. Every observation of matter moving near the horizon, every measurement of light bending or time dilation, becomes a test of our theories. So far, general relativity has passed all of these tests, but physicists remain watchful for even the smallest deviation, a clue that new physics might be waiting to be discovered. One of the most intriguing ideas is that event horizons might not be perfect boundaries at all. Some theories propose that quantum effects could create a thin atmosphere of energetic particles hovering just outside the horizon. Others suggest that the horizon might be replaced by something entirely different, like a fuzzball of tangled strings in string theory, or a firewall of energy that incinerates anything that touches it. These ideas are controversial because they challenge the smooth, featureless horizon predicted by general relativity, but they are taken seriously because they might resolve paradoxes about information loss. And then there is the unsettling possibility that the event horizon could be hiding phenomena we have not even begun to imagine. If wormholes or exotic forms of matter exist, they might be found in the extreme conditions near a black hole. If the holographic principle is correct, the surface of the event horizon could be like a vast cosmic storage drive, holding the history of everything that has ever fallen in. But with no way to retrieve that data, such speculation remains in the realm of theory. For all these reasons, the event horizon stands as both a warning and an invitation. It warns us that there are places in the universe from which no return is possible, but it also invites us to explore the edges of our knowledge, to push our theories to their breaking point, and to imagine realities beyond our own. In this way, the event horizon is not just a dangerous place, it is a boundary in human understanding. In the distant future, when humanity has advanced far beyond its current technology, perhaps we will be able to explore event horizons more directly. We might send probes that can survive longer in their deadly surroundings, or use quantum communication methods to transmit information from the edge in ways we cannot yet conceive. We might even find ways to manipulate space-time itself, skirting the horizon without crossing it. But even in such a future, the fundamental rule will remain: cross the event horizon, and you are gone from our universe. For now, our relationship with event horizons will remain one of careful observation from a safe distance. We will continue to study them using radio telescopes, X-ray observatories, and gravitational wave detectors, piecing together their mysteries from the light and ripples they send our way. Each new observation adds to the picture, making these invisible boundaries just a little less mysterious. but never any less dangerous. The event horizon is the universe's ultimate expression of finality. It is a line that cannot be crossed without consequence, a silent edge where the known gives way to the unknowable. It is a place where time, space, and matter are forever altered, and where the universe itself says, "This far and no farther." Supernova cores, the birthplace of destruction. In the grand theater of the cosmos, few events are as dramatic or as violent as a supernova. These titanic explosions mark the death of massive stars, releasing more energy in a few seconds than our sun will produce in its entire lifetime. But as spectacular as they are when seen from a safe distance, supernovae are also among the most dangerous places in the universe. And at the heart of these cataclysmic events, deep within the core where the explosion is born, lies an environment so extreme that it challenges the limits of our understanding. A supernova's core is not a place that exists for long. It is a fleeting stage in the death of a massive star, lasting only moments before either collapsing into a neutron star or a black hole. But in that short time, the conditions are so intense that matter is pushed into exotic forms. Temperatures soar into the billions of degrees, and atomic nuclei are forged in furious nuclear reactions. The danger here is not in the prolonged exposure to these conditions. No object could survive long enough to experience that, but in the sheer instantaneity of the forces involved. The story begins millions to billions of years earlier, when a star forms from a collapsing cloud of gas and dust. Gravity pulls the material together, heating it until nuclear fusion ignites in the core. For most of its life, the star is in balance. Fusion generates enough pressure to counteract the force of gravity, and the core burns hydrogen into helium. As the star ages and its hydrogen runs out, it begins fusing heavier elements, helium into carbon, carbon into oxygen, and so on, climbing the periodic table. Each new fusion stage releases less energy than the last, and the star must burn hotter and faster to maintain equilibrium. In the final stages for the most massive stars, fusion creates elements like silicon, sulfur, and eventually iron. And iron is a dead end. Unlike lighter elements, fusing iron does not release energy. It consumes it. Once the core is made mostly of iron, the star has no way to generate the pressure needed to resist gravity. The balance tips and the collapse begins. What happens next is unimaginably fast. In less than a second, the iron core, often larger than Earth, implodes. Gravity crushes the atoms so completely that protons and electrons merge into neutrons, releasing a flood of neutrinos. The density skyrockets to the point where a single teaspoon of the material would weigh billions of tons. This sudden collapse halts abruptly when the core reaches neutron star density, creating a kind of rebound effect. The outer layers of the star slam into the newly formed neutron core, and the result is a shockwave that races outward, tearing the star apart in a blinding explosion. The conditions in that collapsing core are among the most hostile in the universe. Temperatures can exceed 100 billion degrees. Pressures are so extreme that normal matter cannot exist. Instead, you find a degenerate sea of neutrons with perhaps even stranger particles, hyperons or quark-gluon plasma, forming in the very center. The burst of neutrinos released in the collapse is so intense that for a fraction of a second, the core outshines the rest of the galaxy in neutrino emission alone. If you were somehow able to witness the collapse from inside the core, you would see matter behaving in ways that seem impossible. Atoms would be torn apart, their nuclei shredded and fused in rapid-fire nuclear reactions. Photons, usually the fastest messengers in the universe, would be trapped, bouncing endlessly among the dense particles. Neutrinos, ghostly particles that normally pass through matter without interaction, would be produced in staggering numbers, billions of times more than in the sun's core, and for once they would interact strongly, transferring energy to the matter around them. The danger of a supernova core is not limited to the collapse itself. The explosion it generates sends a blast wave hurtling outward at thousands of kilometers per second. Any planet in the immediate vicinity is vaporized instantly. Even from dozens of light years away, the radiation from a supernova can be deadly. Gamma rays, X-rays, and high-energy particles can strip away atmospheres, destroy ozone layers, and trigger mass extinctions. In fact, some scientists believe that past supernovae may have played a role in shaping the evolution of life on Earth. The heart of a core collapse supernova is also a factory for the heavy elements that make planets and life possible. Gold, uranium, and many other elements heavier than iron are forged in the intense neutron-rich environment of the explosion. These elements are scattered into space, mixing with gas and dust that will later form new stars and planets. In this way, every living thing is connected to the death of massive stars. The iron in your blood, the calcium in your bones, the gold in a wedding ring. All were made in the hearts of stars and in the violent furnaces of supernovae. But while the poetic notion that we are made of star stuff is true, it should not obscure the fact that a supernova's core is one of the most lethal environments imaginable. It is a place where matter is crushed beyond recognition, where the laws of physics are stretched to their limits, and where energy is released on a scale that dwarfs anything humans can conceive. In just a few heartbeats, a star's core transforms from a stable fusion reactor into a cosmic bomb, reshaping its surroundings for light years in every direction. And for the unlucky objects caught too close, there is no chance of survival. The shockwave, radiation, and particle storms leave nothing intact. Even long after the explosion, the expanding remnant remains hazardous, filled with high-energy particles and magnetic turbulence. This is why astronomers keep close watch on nearby massive stars, to predict when they might explode, and to ensure that no such event threatens our planet in the near future. As the shockwave from the supernova core erupts outward, the physics of destruction become even more staggering. In the first seconds after the core collapse, the blast wave is powered not only by the rebound of infalling matter, but also by the intense flood of neutrinos streaming from the newborn neutron star. Though neutrinos rarely interact with matter under normal circumstances, the density of material just outside the core is so great that even these elusive particles deposit significant amounts of energy, helping to drive the explosion to its full force. Within minutes, the core's immediate surroundings are transformed. Layers of the star that had existed for millions of years are blown apart in a furious cascade, moving outward at speeds reaching tens of thousands of kilometers per second. These layers are stratified according to the elements they contain. Lighter elements like hydrogen and helium near the outside, heavier ones like oxygen and silicon nearer the inside. And in the chaos of the explosion, these materials are hurled into space in all directions. The scale of energy released in these first moments is almost incomprehensible. A typical core collapse supernova radiates as much energy in a few seconds as our sun will produce over its entire 10 billion year lifetime. Most of this energy is carried away by neutrinos, invisible to the eye and nearly impossible to detect, yet so abundant that detectors on Earth have occasionally caught their fleeting presence. In 1987, the supernova known as SN 1987A sent a tiny burst of neutrinos our way, which was detected by specialized underground observatories, a remarkable confirmation of the theory of core collapse. For any nearby planetary system, the devastation is complete. In the inner regions of that system, entire worlds are incinerated in the initial radiation flash. Their surfaces turn to plasma in fractions of a second. Farther out, planets may be stripped of their atmospheres, their surfaces scorched by high-energy photons. The expanding shockwave compresses interstellar gas clouds, altering the structure of the surrounding galaxy. The core itself, in the milliseconds after collapse, becomes the most extreme known environment outside of a black hole. At densities exceeding that of an atomic nucleus, neutrons are packed so tightly that they form a single continuous fluid, a neutron star. This object is only about 20 kilometers across, but contains more mass than the sun. Its surface gravity is so strong that if you dropped a marble from a height of 1 meter, it would hit the surface in a fraction of a microsecond, releasing more energy than a major bomb. In some cases, the core's collapse goes even further, and no neutron star forms at all. If the progenitor star is massive enough, gravity overwhelms even neutron degeneracy pressure, the force that resists the compression of neutrons, and the core continues to collapse into a black hole. In these events, the formation of the event horizon marks the end of any direct evidence of the core's fate. The blast may still occur, powered by the infalling matter, but the core itself is lost forever to the outside universe. Supernova cores are also birthplaces of the heaviest elements. The chaotic environment immediately after collapse is rich in free neutrons, and atomic nuclei rapidly capture them in a process known as rapid neutron capture, or the R process. This process builds up nuclei far heavier than iron in just seconds. These newly forged elements are ejected into space, where they will later be incorporated into future generations of stars, planets, and living beings. This is why scientists often say that supernovae are not just destructive, but also creative. They recycle matter into new cosmic forms. Yet, standing anywhere near such a creation site would be certain death. The energy density, radiation intensity, and matter velocities are beyond any conceivable human shielding. Even robotic probes would be vaporized or torn apart in an instant. The only way we study such events is from light years away, catching the photons and neutrinos that escape and racing to record them before they fade. Supernova cores are also important for what they tell us about the ultimate fate of massive stars. By observing the remnants, whether neutron stars, pulsars, or black holes, we can piece together the violent processes that occur in those final moments. Some neutron stars left behind by core collapse have magnetic fields trillions of times stronger than Earth's, becoming magnetars. Others spin hundreds of times per second, producing beams of radiation that sweep through space like cosmic lighthouses. In either case, the core's transformation marks a permanent change in the local cosmic environment. Where there was once a star providing steady light and warmth, there is now either a dense exotic remnant or an invisible gravitational trap. The surrounding space is littered with shockwave debris, energized particles, and glowing filaments of gas, the supernova remnant, that will expand for tens of thousands of years before fading into the interstellar medium. And while these remnants can be breathtakingly beautiful when seen through telescopes, it is important to remember that they are monuments to unimaginable destruction. They are the ashes left over from one of nature's most violent processes, the record of a stellar death that forever changed its part of the galaxy. In the months and years following the explosion, the core's violence continues to echo across space. The supernova remnant expands outward, a vast shell of hot gas and plasma that glows in multiple wavelengths: radio waves, visible light, X-rays, depending on the energies of the particles within it. This expanding shell plows into the interstellar medium, sweeping up and compressing clouds of gas and dust. In some regions, this compression can trigger the formation of entirely new stars, meaning that the death of one star can directly lead to the birth of others. The remnant's interior remains a hostile environment. Temperatures inside the shock-heated gas can reach tens of millions of degrees, and the region is flooded with cosmic rays, high-energy protons and atomic nuclei accelerated by the blast wave. These cosmic rays will eventually spread throughout the galaxy, some even finding their way to Earth, where they can interact with our atmosphere and be detected by instruments on the ground. Though the flux of such particles from a distant supernova is small, a nearby explosion could dramatically increase the rate, with potentially harmful effects on life. If the core's collapse created a neutron star, that remnant may be visible as a pulsar. These objects rotate rapidly, beaming radio waves, X-rays, or gamma rays from their magnetic poles. As the neutron star spins, its beams sweep through space, producing a regular pulsing signal that can be detected from Earth. Some pulsars are astonishingly precise, with rotational periods that vary by less than a millionth of a second. Others slow down over time, radiating away their rotational energy into space. Magnetars, an even more extreme form of neutron star, possess magnetic fields so intense that they can twist and fracture their own crusts. These fractures release bursts of X-rays and gamma rays that can outshine the entire galaxy for a brief moment. The energy stored in a magnetar's magnetic field is beyond human comprehension, and the slightest disturbance in that field can produce effects detectable across intergalactic distances. In cases where the core collapsed directly into a black hole, the aftermath is even more mysterious. Depending on the details of the collapse, the explosion may be weaker or even fail to occur entirely, resulting in what astronomers call a failed supernova. In such events, the outer layers of the star may simply fall inward, vanishing silently into the newly formed black hole. These failed explosions are hard to detect, but surveys of massive stars have found examples that seem to have disappeared from view without the expected supernova flash. From a danger perspective, supernova cores and their immediate aftermath are a reminder that the universe is not a stable or safe place. On the cosmic timescale, stars live long, steady lives. But when they die in this way, the process is cataclysmic. Any nearby planets are sterilized in an instant, and even distant systems can suffer the consequences of the radiation and particle storms unleashed. For life to thrive, it must be far from such events or shielded in ways nature rarely provides. The remnants of supernova cores are also laboratories for exotic physics. Neutron stars allow scientists to study matter at densities far beyond anything achievable on Earth. The behavior of particles in such conditions can reveal new states of matter, such as quark matter, where neutrons dissolve into their constituent quarks. Detecting such states is challenging, but astronomers can infer their presence from the mass, radius, and cooling rates of neutron stars, as well as from gravitational wave signals when two neutron stars merge. These mergers, in fact, are directly connected to the story of supernova cores. Many neutron stars are found in binary systems, and over millions of years, gravitational interactions can bring them together. When they collide, they produce gravitational waves, ripples in space-time, and unleash another round of heavy element production. In 2017, astronomers detected such a merger both in gravitational waves and across the electromagnetic spectrum, confirming that these collisions are a major source of elements like gold and platinum. But the neutron stars involved in that event were themselves born in supernova cores long before. Thus, each supernova core is part of a much larger cosmic cycle: birth, life, death, and rebirth on a galactic scale. The danger it represents is balanced by its role in creating the very ingredients for new worlds and life. Without these violent deaths, the universe would lack the diversity of elements needed for planets, oceans, and biology. Still, for anything unlucky enough to exist near one in the moment of collapse, the distinction between creative and destructive is meaningless. The power unleashed in a supernova core is total, overwhelming, and inescapable. It is one of nature's most spectacular warnings that, in the universe, creation and destruction are often the same process. Over thousands of years, the expanding shell from the supernova core begins to slow as it sweeps up more interstellar material. But even then, it remains a source of high-energy radiation and shock-heated gas. The remnant can continue to glow brilliantly in X-rays for tens of millennia, gradually fading as its energy disperses into the surrounding galaxy. From a safe distance, these remnants are breathtaking. Delicate filaments of glowing gas, twisting in intricate patterns, illuminated by the light of atoms that were once part of a living star. But the beauty hides the truth. Every wisp of color marks a region where matter was violently torn apart and hurled into the void. Astronomers studying such remnants can read them like forensic evidence from a cosmic crime scene. By analyzing the light emitted from different parts of the expanding shell, they can determine which elements were created in the explosion, how fast the shockwave is traveling, and even how much mass was ejected. These measurements help reconstruct the final seconds of the star's life and reveal the extreme conditions inside the core before it was destroyed. The core's influence extends far beyond the immediate aftermath. In regions where multiple supernovae have exploded over time, their combined shockwaves can carve out vast cavities in the interstellar medium, known as superbubbles. These structures can span hundreds of light years and fundamentally alter the dynamics of star formation in their host galaxies. The edges of these bubbles are often sites of intense starbirth, as compressed gas clouds collapse under their own gravity to form new suns. Thus, the violent deaths of stars can seed the conditions for future generations of stars, and, potentially, planets capable of supporting life. If the remnant contains a neutron star, its rapid rotation and intense magnetic field can power what astronomers call a pulsar wind nebula, a bubble of energetic particles and magnetic fields that glows across the electromagnetic spectrum. The Crab Nebula is a famous example, the remains of a supernova observed on Earth in the year 1054. At its center lies a pulsar spinning 30 times per second, emitting beams of radiation so regular they could be mistaken for a precision timepiece. The energy from the pulsar keeps the nebula shining centuries after the explosion, a lasting reminder of the core's ferocious birth. From a hazard perspective, the energy still pouring out of the core remnant, whether from a pulsar, a magnetar, or an accreting black hole, can pose threats to nearby systems. Gamma-ray bursts, thought to be linked to certain types of supernovae, can unleash beams of energy so intense that they could sterilize planets thousands of light years away if aimed directly at them. While such an event is exceedingly rare in our part of the galaxy, it underscores the lethal potential of massive stellar deaths. One of the most fascinating and unsettling aspects of supernova cores is their unpredictability. While astronomers can identify stars likely to explode within the next few million years, pinpointing the exact moment is almost impossible. A star can appear steady and unchanging for centuries, only to erupt without warning. For civilizations orbiting such a star, there would be no time to prepare. In an instant, their world would be subjected to a level of destruction from which no technology could protect them. Our own sun will never experience such a fate. It is too small to undergo core collapse. But there are stars in our galactic neighborhood that will. Betelgeuse, a red supergiant in the constellation Orion, is one example. When it eventually goes supernova, it will be bright enough to be seen in the daytime sky from Earth, though far enough away that it poses no threat to us. Still, the event will offer an unprecedented opportunity to study a supernova core in action, providing clues about the processes that unfold in those brief, lethal moments. In the end, the core of a supernova is one of the universe's most dangerous places, not because it lasts long, it is gone in an instant, but because of what it unleashes. The collapse of that dense heart sets in motion forces that reshape entire regions of space, forge the raw materials of life, and erase worlds in a heartbeat. It is a reminder that in the cosmos, creation and destruction are often inseparable, each feeding the other in a cycle as old as the stars themselves. And so, in the story of dangerous places in the universe, the supernova core holds a special place. It is both the grave of a star and the cradle of new elements, a furnace where matter is broken and remade under unimaginable pressure and heat. To witness it up close would be to experience the most extreme conditions nature can produce. But it would also be the last thing you ever saw. Magnetar fields, the universe's strongest magnetic traps. In the catalog of dangerous places in the cosmos, magnetars stand out as silent but lethal threats. These are not merely neutron stars, already some of the densest and most extreme objects in existence, but neutron stars with magnetic fields so intense that they defy ordinary comprehension. A typical neutron star already possesses a magnetic field trillions of times stronger than Earth's. A magnetar pushes this to the limit, with a field up to 1,000 times stronger still. In such an environment, the very structure of atoms is distorted, space is saturated with energy, and even the vacuum itself behaves in strange ways. Magnetars are born in the aftermath of massive stellar deaths. When a star, many times the mass of our sun, explodes as a supernova, the collapsing core may form a neutron star. If certain conditions are met, rapid rotation at birth, and the right balance of mass and internal turbulence, the newborn neutron star's magnetic field can be amplified to incredible strengths, creating a magnetar. The physics behind this process is still a subject of research, but the leading idea is that the young star's rapid spin drives a dynamo effect, much like the one that generates Earth's magnetic field, but on an incomparably larger scale. In the first seconds of its life, the magnetar's rotation and internal currents feed its magnetic field until it reaches levels beyond anything else in the universe. To get a sense of scale, Earth's magnetic field measures about half a Gauss in strength. A refrigerator magnet is perhaps a few hundred Gauss. The magnetic field of a typical neutron star is around 1 trillion Gauss. A magnetar? Up to 1 quadrillion Gauss. At that strength, the field could erase every credit card on Earth from halfway to the moon. It could distort the electron clouds of atoms, stretching them into needle-like shapes and altering the very chemistry of matter. If you could somehow approach a magnetar, which in reality you could not, the field would disrupt the electrical bonds in your body, tearing apart molecules before you were even close enough to see it. One of the most dangerous aspects of magnetars is that they do not need to be touched to be lethal. Their magnetic influence extends vast distances, and the energy they release during magnetic disturbances can be catastrophic. Occasionally, a magnetar's crust, the solid outer layer of neutron star matter, can crack under the immense stress of its own magnetic field. When this happens, it triggers what astronomers call a starquake, unleashing a flare of X-rays and gamma rays so intense that it can be detected across the galaxy. The most powerful of these flares can momentarily outshine every other source of X-rays in the Milky Way combined. The 2004 giant flare from the Magnetar SGR-180-6-20 is a sobering example. Located about 50,000 light-years from Earth, it released as much energy in a fraction of a second as the Sun emits in 100,000 years. If such an event occurred within a few light-years of Earth, it could strip away much of our atmosphere, destroy satellites, and severely damage any living organism exposed to the radiation. Fortunately, the known magnetars are far enough away to pose no immediate threat, but the potential is there. From up close, if that were possible, the surface of a magnetar would be an alien landscape. Only about 20 kilometers in diameter, the entire object could fit within a major metropolitan area. Yet its gravity is so strong that a teaspoon of its matter would weigh billions of tons. The surface is likely covered in an iron-rich crust, perhaps fractured and warped by magnetic stresses, with temperatures of millions of degrees. Above it, the magnetic field would twist space itself, bending the paths of charged particles, and even affecting the polarization of light in ways that can be measured by sensitive telescopes. The environment near a magnetar is not just a place of extreme magnetism, but also of intense radiation. The magnetic field funnels particles into beams that can sweep across space as the star rotates, much like the beams from a pulsar. These beams are not ordinary light. They can be high-energy X-rays or gamma rays, deadly to any unshielded life forms. As the magnetar spins, its rotation gradually slows, but the energy stored in its magnetic field can continue to power outbursts for tens of thousands of years. One of the strangest predicted effects of a magnetar's field is vacuum birefringence, a phenomenon in which the empty space around the star acts like a prism, splitting and polarizing light due to the influence of the magnetic field on virtual particles in the vacuum. This is not science fiction. It is a real consequence of quantum electrodynamics, and observations of certain neutron stars have provided tantalizing evidence that it happens. In the most extreme cases, the magnetic field could become so strong that even the quantum vacuum itself is altered, creating conditions impossible to replicate anywhere else. For spacecraft or technology, a magnetar would be a nightmare destination. Electronics would fail instantly, circuits would be fried, and structural materials could weaken under the intense magnetic stress. Even from a safe distance, a sudden flare could overwhelm sensors and communications. No shielding we can currently build would be adequate to survive direct exposure to such an outburst. The danger zone around a magnetar depends on its activity level. A dormant magnetar, one not currently flaring, still has an intense magnetic field, but might not release large bursts of radiation. An active one, however, could fire off repeated flares, each capable of devastating a planet in its vicinity. These events are unpredictable, making magnetars unstable neighbors in the cosmic sense. Magnetars are rare, but their rarity does not make them any less significant in the grand scheme of cosmic hazards. Astronomers estimate that out of the hundreds of millions of neutron stars in our galaxy, only a few dozen are magnetars. This is partly because their extreme magnetic fields decay over time, typically within about 10,000 years. A blink of an eye in astronomical terms. Once the field weakens, the object becomes less violent and eventually resembles a typical neutron star. But during that short active lifetime, a magnetar can produce multiple high-energy outbursts capable of altering its local galactic environment. These outbursts come in different intensities. The most common are short X-ray bursts, lasting less than a second, but releasing enormous amounts of energy. More rare are intermediate flares, which can last several seconds and release more energy than the sun produces in centuries. And then there are the truly exceptional giant flares, events so powerful that they can be detected in galaxies millions of light years away. The 2004 giant flare from SGR 1806-20 was one such event, and it remains one of the most powerful explosions of any kind ever recorded in our own galaxy. The cause of these flares lies in the unstable relationship between the Magnetar's magnetic field and its rigid crust. Over time, stresses build up as the field twists and distorts the crust. When the crust can no longer bear the strain, it cracks, sending shockwaves through the star's outer layers and rearranging the magnetic field lines in a process similar to solar flares on our sun, but on a scale billions of times more energetic. The sudden reconfiguration of these field lines accelerates particles to near light speeds, producing intense radiation across the electromagnetic spectrum. If you could somehow watch this happen from a hypothetical safe distance, the Magnetar would appear to brighten dramatically in high-energy light, flooding space with a torrent of X-rays and gamma rays. The flare would expand outward at the speed of light, bathing anything in its path with lethal radiation. Planets in the Magnetar's system, if they existed, would see their atmospheres ionized almost instantly. Any life forms would be obliterated in a fraction of a second, with no time to react or seek shelter. But the magnetic field of a Magnetar is itself a constant hazard. Even in the absence of a flare, the field strength can reach far enough to influence space hundreds of thousands of kilometers away. In theory, if a Magnetar were within about 1,000 kilometers of Earth, its field could disrupt the chemical bonds in molecules, essentially dismantling matter at the atomic level. Thankfully, the closest known Magnetars are thousands of light years away, far beyond such a catastrophic range. Interestingly, Magnetars may also be linked to one of the most mysterious phenomena in modern astronomy: fast radio bursts, FRBs. These are intense millisecond-long flashes of radio waves that seem to originate from far outside our galaxy, and in some cases, from within it. In 2020, astronomers detected an FRB from a known Magnetar, SGR 1935+2154, providing the first direct evidence that at least some FRBs are produced by these magnetic monsters. The exact mechanism is still debated, but it may involve sudden magnetic reconnections or crustal fractures that channel enormous amounts of energy into coherent radio emissions. The combination of unpredictability, sheer energy, and the ability to affect its surroundings at vast distances makes the Magnetar one of the universe's most efficient natural weapons. Unlike a supernova or a gamma-ray burst, which are tied to specific life stages of stars and occur in particular conditions, a Magnetar can unleash dangerous radiation at almost any point in its active lifetime. The danger isn't constant, but it's always possible. Over geological timescales, a single giant flare from a nearby Magnetar could alter the course of evolution on a habitable planet. By stripping away atmospheric layers, particularly the ozone, such a flare could allow harmful ultraviolet light from the planet's star to reach the surface unimpeded. The result could be mass extinctions, similar to those hypothesized from asteroid impacts, but with no visible impact crater and no warning signs other than a sudden brightening in the sky moments before the devastation. In the extreme physics laboratory of a Magnetar's magnetic field, even the vacuum of space becomes a medium for strange effects. Theories predict that under such field strengths, virtual particle pairs, constantly popping in and out of existence in the quantum vacuum, can align in ways that affect the propagation of light. Observing these effects could provide direct insights into the behavior of matter and energy in conditions impossible to recreate on Earth. This makes Magnetars not only dangerous, but scientifically invaluable for pushing the boundaries of our knowledge. From the perspective of interstellar exploration, a Magnetar would be a prime candidate for long-range observation, but an absolute no-go zone for any crewed mission. Robotic probes might be able to survive brief passes at great distances, collecting data on the star's emissions and magnetic structure, but any attempt to approach too closely would result in instant destruction of electronics, structural systems, and communication equipment. Even at great distances, a Magnetar's presence can shape its local environment in dramatic ways. Its powerful magnetic field can trap and accelerate particles from surrounding space, creating vast magnetospheres filled with high-energy plasma. These magnetospheres act as cages, confining charged particles and guiding them along magnetic field lines toward the star's magnetic poles. When the particles strike the surface near these poles, they release bursts of X-rays and gamma rays, contributing to the star's persistent high-energy glow. The sheer density of matter inside a magnetar adds another layer of danger and intrigue. Beneath the surface crust, already stronger than any material known in the universe, lies a superfluid and superconducting interior where neutrons move without resistance and protons flow in vast currents. These currents help sustain the magnetic field, and in the most extreme cases, they may interact in ways that cause sudden, unpredictable magnetic rearrangements. This is part of why magnetar flares can be so violent and unexpected. The conditions inside are inherently unstable. From a human standpoint, the destructive potential of a magnetar is unmatched in certain respects. Consider the 2004 giant flare from SGR 1806-20 again. At a distance of 50,000 light-years, it still managed to measurably affect Earth's upper atmosphere. That means its energy output was so vast that even after spreading across the enormous expanse of space, enough of it reached our planet to cause detectable changes. If an equivalent event happened within 10 light-years, Earth's surface would be directly exposed to lethal levels of radiation, potentially sterilizing the biosphere. Magnetars also have an unusual way of aging. Unlike most neutron stars, which gradually slow down as they radiate away their rotational energy, magnetars lose rotational speed much more rapidly. This is because their intense magnetic fields act as a brake, radiating energy outward in the form of electromagnetic waves and particle winds. Within just a few thousand years, a magnetar can slow from spinning dozens of times per second to just a few times per second. This rapid spin down is one of the main reasons astronomers believe magnetars have relatively short active lifespans compared to other neutron stars. Despite their short lifetimes, the legacy of magnetars may extend much farther. The remnants of their magnetic activity, the high-energy particles they inject into space, can persist for millions of years, influencing the composition and structure of nearby interstellar regions. In this way, a magnetar can leave an invisible but lasting imprint on its surroundings, long after its magnetic field has decayed to less extreme levels. For alien civilizations, if any exist, the detection of a nearby magnetar might be a reason to avoid settling in certain regions of a galaxy. Just as humans on Earth map out fault lines, flood zones, and hurricane paths, an interstellar society might catalog the positions and activity levels of magnetars to ensure they do not inadvertently place colonies in harm's way. In fact, the unpredictable nature of magnetar flares could make them one of the few natural hazards in the galaxy that even advanced civilizations would have difficulty mitigating. From a scientific perspective, however, the risks are balanced by opportunity. Because magnetars operate under such extreme conditions, they offer a natural testbed for theories of matter, magnetism, and high-energy astrophysics. By studying their emissions, astronomers can probe the structure of neutron star interiors, the behavior of matter in intense magnetic fields, and even aspects of fundamental physics such as quantum electrodynamics. Observations of magnetars have already provided some of the best evidence for vacuum birefringence, a phenomenon that had long been predicted but not directly seen. Yet, in the context of dangerous places in the universe, none of this diminishes their lethality. If a supernova core is the brief or violent end of a star's life, a magnetar is the lingering, volatile aftermath, a compact engine capable of unleashing catastrophic bursts of energy without warning. Its danger lies not just in its power, but in its unpredictability. You can see a supernova coming. You cannot always see a magnetar flare until it's already happening. In the hierarchy of cosmic hazards, a magnetar's field is perhaps the purest form of threat. Invisible, silent, and capable of altering matter itself, no weapon humanity could conceive comes close to the scale of its destructive reach. And yet, for all their danger, magnetars are essential pieces of the cosmic puzzle, teaching us about the limits of physics while reminding us how fragile life is in a universe governed by forces of such unimaginable strength. Gamma-ray burst zones, beams of instant annihilation. If there is one phenomenon in the universe that truly deserves the description instant annihilation, it is the gamma-ray burst, or GRB. These cosmic events are the most energetic explosions we have ever observed, releasing in a few seconds as much energy as our sun will produce in its entire 10 billion year lifetime. They are not just bright, they are blindingly, lethally bright in a very specific part of the electromagnetic spectrum, gamma rays, the most energetic form of light. And because GRBs emit most of their energy in narrow, focused beams rather than in all directions, any unlucky planet in the direct path of one is at risk of complete devastation. Gamma-ray bursts were first detected by accident in the late 1960s, when military satellites designed to monitor nuclear tests picked up mysterious flashes of high-energy radiation coming from deep space. At first, their origin was unknown, and theories ranged from exotic astrophysical events to alien weaponry. It soon became clear, however, that these bursts were natural phenomena occurring far beyond our galaxy. They came in two main types: short-duration bursts, lasting less than 2 seconds, and long-duration bursts, which can last from a few seconds to several minutes. The distinction is not just about timing, it points to different origins. Long GRBs are now believed to be linked to the deaths of certain massive stars, events known as hypernovae. In these rare cases, when a massive star's core collapses into a black hole, the collapse produces twin jets of material and radiation that blast outward along the star's rotational axis at nearly the speed of light. As these jets punch through the outer layers of the star and into space, they produce a gamma-ray burst. If one of these beams happens to be pointed directly at Earth, even from thousands of light years away, the consequences could be catastrophic. Short GRBs, on the other hand, are thought to arise from the mergers of compact objects, such as two neutron stars or a neutron star and a black hole. These collisions release enormous amounts of energy, producing intense bursts of gamma rays and often triggering a kilonova, a fainter but longer-lived explosion that synthesizes heavy elements like gold and platinum. The 2017 detection of gravitational waves from a neutron star merger, followed by a short GRB, confirmed this connection. The sheer power of a GRB comes from the concentration of energy in its narrow beam. Unlike a supernova, which emits light in all directions, a GRB focuses its output into jets that may cover only a few degrees of the sky. This beaming effect means that the energy per unit area in the jet is vastly greater than it would be if spread evenly. If Earth were to be in the path of such a beam, the upper atmosphere would be stripped away in seconds, and the surface would be bathed in intense gamma radiation. The destruction would not come from heat or blast, but from the deep molecular damage caused by high-energy photons. DNA shattered, ecosystems collapsing, and the planet's protective ozone layer gone. The distances involved in most observed GRBs are so great that we are safe from their effects. But there is evidence that one or more GRBs may have struck Earth in the distant past, possibly contributing to mass extinctions. Geological records show hints of sudden spikes in certain isotopes that could be explained by such an event, though the evidence remains circumstantial. Even so, the possibility is sobering. A GRB does not need to be close in astronomical terms to be deadly. A burst from a few thousand light years away, if aimed directly at us, could wreak havoc. From a visual perspective, if you could see gamma rays with your eyes, a GRB in your direction would not be a slow, dramatic show. It would be a sudden, blinding flash that fills the sky, followed by a rapid dimming as the afterglow fades in X-rays, ultraviolet, visible light, and eventually radio waves. The whole event, from start to finish, might last only minutes, but its effects could linger for years or centuries. For spacecraft or explorers in deep space, the danger of GRBs lies in their unpredictability. While astronomers can identify regions and stellar systems where conditions are ripe for a GRB, for example, galaxies with many massive, rapidly rotating stars, predicting the exact timing is impossible. A ship in the wrong place at the wrong time could be caught in a burst with no warning, its electronics fried and crew fatally irradiated before they could react. The afterglow of a GRB is almost as scientifically important as the burst itself. Observing how the radiation changes over time gives astronomers clues about the density of the surrounding space, the energy of the jets, and the nature of the explosion that produced them. In some cases, the afterglow is bright enough in visible light to be spotted with small telescopes, even from billions of light years away, a testament to the power of the initial burst. One of the most unsettling aspects of GRBs is how they combine two qualities that make them exceptionally dangerous: enormous destructive power and narrow beaming. The beam means they are rarer in terms of hitting any given point, but it also means that if you were in the line of fire, the dose of radiation is far higher than it would be from a more diffuse explosion. It's like the difference between being warmed by the sun's rays and being burned by a laser. The energy per unit area is vastly greater in the latter case. The environments where gamma-ray bursts are born are themselves some of the most hostile regions in the universe. For long-duration GRBs, the progenitor stars are often Wolf Rayet stars, massive evolved stars stripped of their outer hydrogen layers, burning at incredibly high temperatures and rotating rapidly. These stars end their lives with enough angular momentum to channel collapsing material into the narrow, relativistic jets that define a GRB. In the moments before the burst, the core of the star collapses into a black hole or a highly magnetized neutron star called a magnetar, and the infalling matter feeds the newly formed object, powering the jets from deep within. The jets themselves are made of ultra-relativistic plasma, particles accelerated to speeds within a tiny fraction of the speed of light. This means that even small amounts of matter in the jets carry staggering amounts of kinetic energy. As they break through the outer layers of the star, they produce shock waves that accelerate photons to gamma-ray energies. For a distant observer in the beam's path, all of that energy arrives almost simultaneously, creating the intense, short-lived pulse we detect as a GRB. Short-duration GRBs, originating from mergers of neutron stars or neutron stars with black holes, occur in very different environments. Such mergers are the final act in a long gravitational dance, often taking hundreds of millions or billions of years. Over this time, the objects spiral closer together, radiating gravitational waves until they finally collide. The collision compresses matter to densities beyond those found in neutron star cores, potentially creating exotic phases of matter like quark-gluon plasma for a fleeting moment. The violence of the merger launches jets along the system's rotational axis, and if one of these jets is aimed at us, we see a short GRB. The potential danger to Earth from a GRB depends not only on the distance, but also on the energy of the burst and the alignment of the jet. Astronomers estimate that a GRB within about 6,000 to 10,000 light-years, pointed directly at Earth, could be devastating to life. The initial gamma-ray flash would be followed by an ultraviolet and X-ray afterglow that could persist for days or weeks, prolonging the atmospheric damage. Without the ozone layer, solar ultraviolet radiation would flood the surface, killing plankton in the oceans, collapsing food chains, and triggering mass extinctions. There are certain stars in our galaxy that could, in theory, produce such an event. One often cited example is WR104, a Wolf Rayet star about 7,500 light-years away. It appears to have a rotational axis roughly aligned with Earth, leading to speculation that it could one day send a GRB in our direction. However, current studies suggest the alignment may not be exact, and the star may not have all the necessary conditions for a GRB. Still, the fact that astronomers even consider the possibility highlights the need to understand these events. From a spacecraft's perspective, being caught in a GRB would be like being placed inside the beam of the most powerful particle accelerator imaginable. The radiation would overwhelm shielding, fry electronics, and kill any crew instantly. The energy density is so high that even spacecraft components made of the strongest known materials would suffer molecular-level damage. In effect, there is no safe distance for an unprotected ship inside the direct beam. Only being outside the beam's path offers safety. GRBs are also of enormous interest to cosmologists because they are so bright they can be seen across most of the observable universe. This means they can serve as beacons, allowing scientists to study the conditions of the early cosmos. Light from a gamma-ray burst carries information about the galaxies it passes through, letting astronomers probe the gas content, chemical composition, and structure of regions billions of light-years away. In this way, events that are deadly up close become invaluable tools from afar. However, the same beaming that makes GRBs so useful to observers also means that we see only a fraction of the bursts that actually occur. For every GRB we detect, there may be hundreds or thousands more happening in other directions. The universe could be filled with these lethal beams, each sweeping through space without regard for what might lie in their path. For life on a planet within range of a gamma-ray burst, the sequence of destruction would be swift and merciless. The initial flash of gamma rays would last anywhere from milliseconds to a few minutes, depending on whether it was a short or long burst. In that time, high-energy photons would slam into the planet's atmosphere, breaking apart molecules and creating a flood of nitrogen oxides. These compounds would rapidly react with ozone, tearing apart the thin shield that protects the surface from the sun's ultraviolet radiation. The burst itself would also produce an intense shower of secondary particles as gamma rays collided with atmospheric nuclei, generating cascades of electrons, positrons, and muons. Many of these particles could reach the ground, delivering direct radiation doses to living organisms. In the oceans, plankton, the foundation of the marine food web, would suffer catastrophic losses, triggering a chain reaction of ecosystem collapse. On land, plants and animals would be exposed to levels of UV radiation far beyond what they could tolerate, leading to massive die-offs. The devastation would not be confined to biology. Atmospheric chemistry would shift dramatically, with the destruction of ozone allowing more UV to reach the surface for years after the burst. Nitrogen oxides would also contribute to acid rain, further stressing ecosystems already reeling from the radiation. The climate could cool temporarily as aerosols formed in the atmosphere, altering how much sunlight reached the surface. These combined effects could plunge the planet into a prolonged ecological crisis, even if the GRB itself lasted only seconds. Some scientists have suggested that GRBs might explain certain mass extinctions in Earth's history. One candidate is the Ordovician-Silurian extinction about 450 million years ago, which wiped out a significant portion of marine life. Evidence for this includes isotopic anomalies that could be explained by atmospheric reactions to intense radiation, though direct proof remains elusive. Whether or not GRBs have played a role in our planet's history, the fact that they could is a reminder of their destructive reach. The danger zone for a GRB is vast. Even from thousands of light years away, the beam can deliver enough energy to damage or strip a planet's atmosphere. And because the beam is so narrowly focused, there is no advance warning unless astronomers happen to be monitoring the exact region of sky from which the burst will come. This unpredictability means that civilizations, human or otherwise, would have little chance to take evasive action. Unlike asteroids or nearby supernovae, which can often be predicted long in advance, a GRB arrives without announcement. In regions of the universe with high rates of star formation, GRBs may be more common. This could have profound implications for the development of life. Some researchers have speculated that GRBs might help explain the Great Silence, the apparent absence of detectable extraterrestrial civilizations. In areas too frequently swept by these beams, complex life might never have the chance to evolve or survive long enough to build advanced societies. In this way, GRBs could act as a form of cosmic population control, setting limits on where and when life can flourish. Ironically, what makes GRBs deadly also makes them scientifically precious. Because they are so luminous, they can be detected across almost the entire observable universe. Some GRBs we see today occurred more than 13 billion years ago, when the first stars and galaxies were forming. By studying their light, astronomers can probe the conditions of the early cosmos in a way no other object allows. In effect, GRBs are both destroyers and messengers, annihilating worlds up close while carrying valuable information to observers far away. From an engineering standpoint, Surviving a GRB in deep space would require a level of shielding far beyond anything humans can currently produce. Even burying a habitat under kilometers of rock or ice might not be enough to block the most intense bursts. The only truly effective defense is not to be in the beam's path at all, which, given the beam's narrowness and unpredictability, is more a matter of luck than planning. Some of the most remarkable and terrifying the features of gamma-ray bursts lie in the physics of their jets. These jets are composed of plasma moving at ultra-relativistic speeds, meaning that the particles are traveling so close to the speed of light that relativistic effects dominate their behavior. At these velocities, time dilation and length contraction become significant, and the kinetic energy of the particles is amplified to levels beyond what even our most powerful particle accelerators can produce. Inside the jet, shock waves form as faster-moving material catches up with slower-moving layers, converting kinetic energy into radiation. These internal shocks are one of the primary mechanisms thought to generate the gamma rays we detect. Farther out, as the jet slams into the surrounding interstellar medium, external shocks form, producing the afterglow that can be observed for days, weeks, or even months in X-rays, visible light, and radio waves. The afterglow serves as a kind of cosmic autopsy, revealing details about the burst's environment and the energy of the explosion. The collimation, or focusing, of these jets is critical to their power. If the same amount of energy were radiated in all directions, it would be far less destructive at great distances. But by concentrating their output into beams just a few degrees wide, GRBs deliver a lethal dose of radiation to anything in their path. This beaming also means that for every gamma-ray burst we observe, there may be hundreds more occurring in other directions, invisible to us, but just as deadly to whatever worlds lie in their crosshairs. One fascinating aspect of GRB research is the connection between these bursts and the formation of heavy elements. In neutron star mergers, the same cataclysm that produces a short GRB also creates conditions for rapid neutron capture, or R-process nucleosynthesis, which forges elements like gold, platinum, and uranium. These elements are then dispersed into space, enriching future generations of stars and planets. It is a strange irony that the same event capable of sterilizing a planet could also be responsible for creating the materials that might someday make another planet habitable. There is also an important link between GRBs and gravitational waves. When compact objects merge, they send ripples through space-time that can be detected by observatories like LIGO and Virgo. If a GRB is observed in coincidence with a gravitational wave signal, it allows scientists to triangulate the event's location and study it in unprecedented detail. The 2017 neutron star merger provided just such an opportunity, offering a glimpse into both the violent physics of the merger itself and the broader astrophysical context of GRBs. For all their destructive potential, GRBs also serve as tools for exploring the universe's most distant reaches. Because they are visible from so far away, they can act as cosmic lighthouses, illuminating the space between galaxies and allowing astronomers to study the distribution of matter on the largest scales. In some cases, the light from a GRB has passed through multiple galaxies on its way to Earth, picking up spectral signatures that reveal information about those galaxies' compositions and motions. Still, when considered from the perspective of planetary safety, GRBs are among the most dangerous phenomena the universe has to offer. The narrowness of their beams makes them relatively rare threats to any given world, but when they do strike, the effects are unmatched in their speed and completeness. Unlike a supernova, which may give nearby civilizations years or even centuries of warning, a GRB offers no advance notice. The first sign of danger is the arrival of the radiation itself, by which time it is far too late to act. In that sense, GRBs are the ultimate cosmic snipers, unseen, silent, and capable of delivering a killing blow from unimaginable distances. They are reminders that in the vast expanse of space, safety is often an illusion, and that even in the emptiest regions of the cosmos, unseen dangers can lie in wait. Quasar hearts, the blazing centers of active galaxies. If the universe has showpieces, cosmic stages upon which the most spectacular light shows occur, then quasars are its grandest performances. They are the blazing hearts of active galaxies, powered by supermassive black holes devouring matter at ferocious rates. From distances of billions of light years, quasars can outshine the combined light of every star in their host galaxy. But their beauty is inseparable from their danger. Up close, a quasar's central engine is one of the most inhospitable environments imaginable. A maelstrom of radiation, magnetic fields, and high-energy particles swirling around a gravitational abyss. Quasars, short for quasi-stellar radio sources, were first identified in the 1960s as mysterious points of light emitting intense radio waves. At first, astronomers didn't understand their nature. They appeared star-like in telescopes, but had incredibly large redshifts, indicating they were extremely far away. To be visible from such distances, they had to be generating energy on an unprecedented scale. It was eventually realized that quasars are the luminous cores of galaxies whose central supermassive black holes are actively feeding on vast amounts of gas and dust. The basic structure of a quasar begins with the supermassive black hole at the center, an object with a mass ranging from millions to tens of billions of suns. Surrounding it is an accretion disk, a flattened whirlpool of superheated gas spiraling inward. As matter falls toward the black hole, it is compressed and heated to millions of degrees, releasing enormous amounts of radiation across the electromagnetic spectrum. Above and below the disk, powerful relativistic jets may form, shooting out streams of particles at nearly the speed of light. These jets can extend for hundreds of thousands of light years, sometimes far beyond the boundaries of the host galaxy itself. The danger zone around a quasar's heart extends far beyond the immediate vicinity of the black hole. The radiation output from the accretion disk is so intense that it can sterilize planets thousands of light years away. Ultraviolet and X-ray emissions are particularly deadly to living organisms, and the sheer brightness can overwhelm the skies of any nearby worlds. If Earth were placed within a few thousand light years of an active quasar, our atmosphere would be stripped away in short order, and the surface would be bathed in lethal radiation. The scale of energy involved is almost beyond comprehension. A typical quasar can produce 10 to 100 times the energy of the entire Milky Way galaxy, but concentrated in a region only a few light days or light weeks across. This energy output is not steady. Quasars can flare and dim over days, weeks, or years as the flow of material into the black hole changes. For civilizations within range, these fluctuations would mean unpredictable surges in radiation, each potentially catastrophic. The accretion disk itself is a place of unimaginable extremes. Temperatures reach millions of degrees, and the disk is threaded with magnetic fields that twist and snap, launching hot plasma into space. Matter in the inner disk orbits so fast, sometimes a significant fraction of the speed of light, that relativistic effects change its appearance, causing one side of the disk to appear brighter due to Doppler boosting. Any spacecraft venturing into such a region would be destroyed long before approaching the horizon of the black hole, fried by radiation and torn apart by tidal forces. One of the defining features of quasars is their jets. These twin beams of particles, accelerated to nearly light speed, are thought to form when magnetic fields near the black hole's poles channel plasma outward. While the exact mechanism is still debated, it is clear that these jets carry enormous amounts of energy. If one were pointed directly at Earth, the effects could be similar to, or even worse than, those of a gamma-ray burst, sustained over much longer timescales. The jets can also impact the evolution of their host galaxies, blowing away gas that would otherwise form new stars. From a safe cosmic distance, quasars are valuable tools for astronomy. Because they are so bright, they can be seen across most of the observable universe, making them markers for measuring cosmic expansion and probing the intergalactic medium. Light from a quasar often passes through intervening galaxies and gas clouds on its way to us, picking up absorption lines that reveal the composition and structure of the universe along the line of sight. But for any planet unlucky enough to reside in the same galaxy and near the central engine, the quasar's heart is a zone of certain doom. The gravitational environment near the black hole warps space and time so severely that stable orbits can only exist far from the core. Closer in, intense radiation pressure and magnetic turbulence would strip atmospheres, melt surfaces, and render even the most advanced shielding useless. Closer to the core of a quasar, the scale of violence becomes difficult to describe in familiar terms. The innermost regions of the accretion disk, sometimes only light hours across, are the engines driving the quasar's brilliance. Here, matter spirals inward at a significant fraction of the speed of light, colliding with other infalling material, creating shock waves and heating to temperatures where atoms are stripped entirely of their electrons. The resulting plasma radiates fiercely, producing a blinding glare that can outshine all the stars in the host galaxy combined. The magnetic fields in this zone are extraordinarily strong, twisted and contorted by the differential rotation of the disk. These fields not only help to launch jets, but also create magnetic turbulence within the disk itself. This turbulence stirs the plasma, increasing friction and heating, which in turn drives even more radiation. The entire process is a feedback loop. The hotter the disk, the faster material falls inward, and the more energy is released. For anything unfortunate enough to wander into this region, survival is not just unlikely, it is impossible. The radiation dose in the inner quasar zone would be many orders of magnitude beyond lethal levels for any known life form. The intense particle flux would fry electronics instantly, and the gravitational gradient near the black hole's event horizon would pull apart spacecraft or planets in a process similar to spaghettification. Even the mere approach toward this environment would be heralded by a lethal bombardment of X-rays and gamma rays long before tidal forces could take hold. The jets emerging from a quasar's poles are perhaps its most far-reaching and dangerous features. These relativistic streams of particles can travel for millions of light years, carrying away energy equivalent to trillions of nuclear bombs every second. Along their path, the jets slam into interstellar and intergalactic gas, creating vast radio lobes that can stretch beyond the visible limits of the galaxy. If a planet or spacecraft were to be caught in one of these jets, the particle bombardment would be constant and devastating, stripping atmospheres and irradiating surfaces. In some cases, the orientation of a quasar's jet toward Earth creates what is known as a blazar, an active galactic nucleus whose jet is pointed almost directly at us. Blazars are among the most variable and energetic sources of radiation in the sky, capable of brightening and fading dramatically over short timescales. Thankfully, no blazar lies close enough to threaten Earth, but the existence of such objects underscores how orientation can turn a distant hazard into a potential cosmic sniper. Even at galactic scales, the energy output of a quasar can reshape its surroundings. Radiation pressure from the accretion disk and jets can drive galactic winds, streams of gas moving at thousands of kilometers per second, that blow material out of the galaxy's central regions. This can halt star formation in the galaxy's core, effectively regulating the galaxy's growth. In extreme cases, quasars may strip entire galaxies of the raw material needed for new stars, leaving behind a population of aging stars with no young replacements. From a cosmological perspective, quasars are both destructive and creative forces. They can suppress star formation locally, while enriching the intergalactic medium with heavy elements created in earlier stellar generations. The interplay between their destructive jets and their role in galaxy evolution is a key area of research in astrophysics today. If humans were ever to attempt intergalactic travel, regions near active quasars would be marked as high-risk zones, places to avoid at all costs. Any habitable world within a few thousand light years of such a core would face extreme challenges in sustaining life, and even advanced civilizations might find it impossible to protect themselves from the sustained radiation of an active quasar. At distances far from the central black hole, a quasar can still exert profound influence over its host galaxy. The radiation streaming outward from the accretion disk and jets bathes the surrounding interstellar medium in the high-energy light, heating gas clouds to the point where they can no longer collapse to form stars. This process, called quasar feedback, can essentially shut down star formation on a galactic scale, transforming a once vibrant spiral galaxy into a more quiescent elliptical one over millions of years. This feedback is not always destructive in the long run, While the immediate effect is to blow out or heat the gas, the material ejected by the quasar eventually mixes with the intergalactic medium. Over vast timescales, this enriched material can fall back into galaxies, seeding them with heavy elements and potentially fueling later waves of star formation. In this way, quasars act as both the destroyers and the recyclers of galactic ecosystems. Closer to the heart of the quasar, however, there is no reprieve from its violence. The innermost regions of the accretion disk are unstable, with material spiraling inward in a chaotic, turbulent flow. The combination of extreme gravitational forces, intense magnetic fields, and high-speed collisions turns this zone into an astrophysical blender, shredding anything unlucky enough to drift into it. As the disk matter moves inward, it releases gravitational potential energy. And because of the black hole's enormous mass, the amount of energy released per unit of mass is staggering. Just a single grain of sand falling into the disk would release as much energy as an entire city consumes in a year. The light we see from quasars has often traveled for billions of years to reach us, meaning we observe them as they were in the early universe. This makes them invaluable tools for understanding cosmic history. By studying quasars, astronomers have learned that supermassive black holes and their host galaxies evolved together, influencing each other's growth. In some cases, the black hole's feeding activity seems to regulate the galaxy's structure. In others, galaxy mergers appear to trigger the rapid feeding that ignites a quasar. One of the strangest and most dangerous aspects of quasars is the scale of their variability. Some can change in brightness by significant factors over just a few days, a sign that massive shifts are occurring in their accretion flows. Such sudden changes could mean unpredictable swings in the intensity of radiation and particle outflows. For planets within range, such variability would make survival even more difficult, as periods of relative calm could be shattered without warning by bursts of intense radiation. The danger zone around a quasar is not just a matter of distance from the black hole. It also depends on the orientation of its jets and the density of its surrounding environment. A planet far enough away to avoid direct irradiation could still suffer from secondary effects, such as the heating of nearby gas clouds or the impact of shock waves driven by galactic winds. These indirect consequences could alter climates, strip atmospheres, or trigger geological upheavals. For deep space explorers or probes, passing through the vicinity of an active galactic nucleus like a quasar would be among the most hazardous journeys imaginable. Radiation shielding would need to be orders of magnitude more effective than anything we have today. And even then, the risk from high-energy particles might make such a mission suicidal. Navigation near such a region would also be perilous, as the gravity of the central black hole distorts space-time, making trajectories complex and unpredictable. From our safe vantage point on Earth, quasars are distant wonders, brilliant markers of the young universe and the growth of galaxies. But for any civilization unlucky enough to orbit within the inner reaches of an active quasar's galaxy, the core would be a constant, unavoidable threat, radiating death across thousands of light years. The sheer diversity of quasar types adds further complexity to understanding their danger. Some quasars are relatively quiet, with weaker jets or lower feeding rates, while others, especially blazars, unleash torrents of energy directly toward us. Blazars are essentially quasars whose relativistic jets are pointed almost exactly in our direction, making them appear far brighter and more variable. The beaming effect not only increases the apparent luminosity, but also concentrates the radiation, turning an already dangerous source into something even more formidable. If a blazar were located within our own galaxy and pointed directly at Earth, the consequences would be dire. The gamma rays and high-energy particles streaming from the jet could strip away Earth's atmosphere and bathe the surface in lethal radiation. The event would be sustained, unlike a gamma ray burst, meaning the radiation would continue for as long as the jet remained active, potentially thousands or millions of years. Any life on the planet would either be driven underground or into extinction. The feeding habits of quasars are another key factor in their danger profile. The amount of material a supermassive black hole consumes can vary widely, and when large amounts of gas and dust fall inward at once, perhaps triggered by a galaxy merger, the quasar can flare dramatically in brightness. This surge in activity can drastically expand the danger zone, flooding nearby regions with far more radiation than they normally receive. In the most extreme cases, the quasar's luminosity can increase by an order of magnitude over a short time, turning a marginally survivable environment into a death trap. Quasars also reshape their galaxies through mechanical as well as radiative feedback. The powerful winds they drive can compress gas clouds in some areas, triggering bursts of star formation, while sweeping gas away from others, shutting star formation down entirely. These processes create a patchwork of life potential within a galaxy, zones where conditions might briefly favor habitability, and others where life is impossible due to constant bombardment by radiation and particles. The jets from quasars remain one of their most dramatic features. Traveling at nearly the speed of light, they carry enormous kinetic energy into intergalactic space. As these jets plow into surrounding material, they inflate colossal lobes of hot plasma, visible in radio wavelengths. These lobes can be hundreds of thousands of light years across, making them some of the largest single structures in the universe. Any star system lying in the path of one of these jets would be subjected to an unending storm of high-energy particles. For astronomers, quasars are both a blessing and a challenge. Their brightness allows them to serve as cosmic lighthouses, revealing the structure of the universe over vast distances. But interpreting their light requires untangling the effects of extreme gravitational fields, relativistic motion, and turbulent accretion flows. Every quasar is a puzzle, and solving these puzzles often reveals new layers of complexity about how galaxies and black holes co-evolve. For hypothetical interstellar travelers, avoiding quasar danger zones would be a matter of necessity. Star maps would need to mark not only the locations of active galactic nuclei, but also the orientations of their jets and estimates of their variability. Passing within a few thousand light years of a powerful quasar would carry risks no technology could yet counter. In the cosmic hierarchy of dangerous places, quasars rank high not only for their immediate lethal potential, but also for their far-reaching influence. They can sterilize regions of space, alter the course of galaxy evolution, and, in extreme cases, flood intergalactic space with high-energy particles. From the relative safety of our current location, they remain distant and beautiful, but up close, they are the blazing, merciless hearts of their galaxies. Cosmic ray storms, the universe's high-energy bullets. Space, despite its vast emptiness, is far from peaceful. Invisible streams of high-energy particles, mostly protons and atomic nuclei, constantly race through the cosmos at nearly the speed of light. These particles, collectively known as cosmic rays, come from a variety of sources: exploding stars, active galaxies, and even violent events in the early universe. While Earth's magnetic field and atmosphere shield us from much of their impact, cosmic rays remain one of the most persistent and dangerous phenomena in the universe. The term cosmic rays is somewhat misleading because these particles are not rays of light, but rather matter, moving at extreme speeds. Most are protons, the positively charged particles found in atomic nuclei, but many are helium nuclei, alpha particles, and heavier atomic nuclei stripped of their electrons. A smaller fraction are high-energy electrons or other exotic particles. Some cosmic rays have relatively modest energies, while others, called ultra-high-energy cosmic rays, carry energies millions of times greater than those achieved in the most powerful human-made particle accelerators. When these high-energy bullets slam into a planet's atmosphere, they collide with atoms and molecules in the air, producing showers of secondary particles such as muons, pions, and gamma rays. These cascades can penetrate deep into the atmosphere and even reach the surface. In space, without the protection of an atmosphere, cosmic rays strike directly, bombarding any exposed object. Whether it's a spacecraft, an astronaut, or a planet with little or no magnetic shielding. The origins of cosmic rays vary. Many are produced by supernova remnants, where shock waves accelerate charged particles to near-light speeds through a process known as diffusive shock acceleration. Others may originate from the jets of active galactic nuclei, where powerful magnetic fields fling particles outward across intergalactic distances. The most energetic cosmic rays, whose origins remain mysterious, could be produced by cataclysmic events such as gamma-ray bursts or collisions between galaxy clusters. For living organisms, the danger of cosmic rays lies in their ability to penetrate biological tissue and damage DNA. At low doses, this damage may simply increase the risk of cancer over time, but at high doses, such as those encountered during strong solar storms or near certain cosmic ray sources, the effects can be acute and lethal. Astronauts outside of Earth's protective magnetic field are especially vulnerable. In deep space, a sustained cosmic ray bombardment could cause radiation sickness within days, long before more subtle effects like cancer could develop. Cosmic rays also pose a major hazard to technology. High-energy particles can cause single-event upsets in electronics, flipping bits in computer memory, or triggering malfunctions in spacecraft systems. Over time, this radiation can degrade materials, weakening structural components and making them more prone to failure. For missions to Mars or beyond, protecting astronauts and electronics from cosmic rays is one of the biggest engineering challenges we face. The storms of cosmic rays are not evenly distributed throughout space. Near active cosmic ray sources such as supernova remnants or pulsar wind nebulae, the density of high-energy particles can be far greater than average. A spacecraft passing near such a source would be subjected to an intense barrage of radiation, requiring shielding far beyond our current capabilities. Even within our own solar system, cosmic ray intensity varies with the 11-year solar cycle, as the sun's magnetic field modulates the flow of particles into the inner planets. While cosmic rays constantly bombard Earth, our planet's magnetic field deflects many of them, guiding them toward the poles where they can interact with the atmosphere to create auroras. The atmosphere itself absorbs most of the energy from those that do get through, but even at sea level, a faint drizzle of secondary particles reaches us, a subtle reminder that space is never truly calm. In the grand scale of cosmic hazards, cosmic ray storms may lack the sudden, cataclysmic drama of a gamma-ray burst or supernova, but their danger lies in their relentlessness. They are always present, always moving, and always capable of causing harm over time. For planets without strong magnetic fields or thick atmospheres, the constant rain of high-energy particles can strip atmospheres away, erode surfaces, and sterilize exposed life forms. In deep space, far from the protective cocoon of a planet's magnetic field and atmosphere, the full intensity of cosmic ray storms becomes apparent. Every particle that strikes is like a tiny bullet, but unlike ordinary bullets, these are moving at relativistic speeds, packing enormous kinetic energy into an atomic-scale projectile. When such a particle slams into the hull of a spacecraft, it can punch through layers of metal, ionizing atoms and creating a trail of secondary radiation that spreads far beyond the initial impact point. This effect, known as secondary showering, is one of the most insidious dangers of cosmic rays for astronauts. Even if the initial particle is stopped by shielding, the collision can produce a spray of secondary particles, often more harmful than the original cosmic ray, that pass through living tissue and damage cells. Over time, cumulative exposure can lead to cataracts, neurological damage, and increased cancer risk. For missions lasting months or years, like voyages to Mars or deep space exploration, the dose of cosmic radiation could exceed current safety limits many times over. The problem is compounded by the fact that cosmic rays are highly penetrating. Shielding against them is far more challenging than blocking ordinary electromagnetic radiation like X-rays or gamma rays. Dense materials such as lead can stop some cosmic rays, but they also generate more harmful secondary particles upon impact. Lighter materials rich in hydrogen, like polyethylene or water, are more effective at slowing down cosmic rays without producing as many dangerous byproducts. But even these are not perfect solutions. Designing a spacecraft with adequate cosmic ray shielding without making it too heavy to launch remains one of the great engineering puzzles in space travel. On a planetary scale, cosmic rays can have dramatic long-term effects on habitability. Planets without strong magnetic fields, like Mars, are constantly bombarded, which over geological timescales can strip away their atmospheres. This happens because cosmic rays, along with the solar wind, can ionize atmospheric molecules, allowing them to be swept into space. Without a protective blanket of air, a planet becomes even more vulnerable to radiation. creating a vicious cycle that can turn once habitable worlds into barren wastelands. Cosmic ray intensity can also spike dramatically in certain environments. Near the shock front of a supernova remnant, for example, the density of high-energy particles is far greater than in interstellar space. These regions are dangerous not just for life, but for any physical object. Spacecraft structures, electronics, and even planetary surfaces can be altered by the relentless impacts. If a supernova were to explode within a few dozen light-years of Earth, the cosmic ray storm it produced could last for tens of thousands of years, bathing our solar system in radiation levels far higher than the current background. Another intriguing and alarming possibility is that some ultra-high energy cosmic rays originate from far more distant and powerful sources, such as active galactic nuclei or gamma-ray bursts. These particles travel across vast stretches of the universe, sometimes carrying energies above 10 to the power of 20 electron volts. Energies so extreme that their exact origins remain one of the great mysteries of astrophysics. When one of these rare particles hits Earth's atmosphere, it sets off an air shower spreading over many square kilometers, detectable by specialized observatories on the ground. For planetary ecosystems, a sustained increase in cosmic ray intensity could alter cloud formation, atmospheric chemistry, and climate. There is ongoing debate among scientists about whether variations in cosmic ray flux have played a role in Earth's climate changes over geological history. While the evidence is not conclusive, it remains a fascinating reminder that cosmic rays may have subtle, far-reaching effects beyond their immediate hazards to life and technology. In the hierarchy of dangerous cosmic environments, cosmic ray storm zones, such as those surrounding pulsars, supernova remnants, or active galactic nuclei, occupy a special place. They are not the quick, dramatic assassins of the cosmos like gamma-ray bursts, but rather the slow, relentless killers. They erode, they mutate, they strip away the protective layers of worlds, and they leave behind the kind of invisible damage that can quietly determine whether life can exist at all. Some of the most dangerous cosmic ray environments are found in the aftermath of violent stellar events. When a massive star explodes as a supernova, its shockwave propagates outward at thousands of kilometers per second, sweeping up interstellar gas and compressing magnetic fields. These conditions create natural particle accelerators on a scale no human technology could hope to match. Charged particles spiral around the amplified magnetic fields, gaining more and more energy with each pass across the shock front. Over thousands of years, this process fills the surrounding space with a dense cloud of high-energy cosmic rays. A spacecraft entering such a region would be exposed to radiation levels far beyond anything encountered in normal interstellar space. Electronics would fail quickly, and human crews, even with heavy shielding, would receive fatal doses in days or weeks. These supernova-generated cosmic ray zones can persist for tens of thousands of years, long after the initial explosion's light has faded from view. In a way, the real hazard of a nearby supernova is not the initial flash of light or heat, but the centuries-long storm of invisible particles that follows. Pulsars, rapidly spinning neutron stars left behind by supernova, are also prolific sources of cosmic rays. Their powerful magnetic fields and rapid rotation act like gigantic particle accelerators, hurling electrons, positrons, and other charged particles into space at extreme energies. Around some pulsars, these outflows form pulsar wind nebulae, vast glowing clouds of energetic particles trapped in the star's magnetic influence. These nebulae are dazzling to observe from afar, but deadly within. Any spacecraft attempting to cross such a zone would be battered continuously by radiation levels that would overwhelm current shielding methods. Even more extreme environments exist near active galactic nuclei and their relativistic jets. Here, particles are accelerated not just to high energies, but to ultra-high energies, the very limits of what is physically possible. These particles can travel for millions of years across intergalactic space before striking a target. The fact that Earth has been hit by such ultra-high energy cosmic rays tells us that somewhere in the universe, natural accelerators are operating at unimaginable power levels. For a planet unlucky enough to orbit close to one of these sources, The cosmic ray environment would make the surface uninhabitable, even underground. One of the subtler dangers of cosmic rays is their ability to trigger chemical reactions in planetary atmospheres. When cosmic rays collide with atmospheric molecules, they can produce reactive species that break down ozone, much like the effects of a gamma ray burst, but on a longer timescale. This thinning of the ozone layer allows more ultraviolet radiation from the planet's star to reach the surface, slowly increasing mutation rates and cancer risks for surface life. Over millions of years, such a process could change the evolutionary trajectory of entire biospheres. Interestingly, cosmic rays might also influence cloud formation by ionizing small particles in the atmosphere, which then act as nuclei for water droplet formation. This link between cosmic rays and climate is still debated, but if it is real, it means that variations in cosmic ray flux could subtly alter weather patterns and long-term climate stability. For planets near variable cosmic ray sources, this could mean climate shifts far more abrupt than those caused by natural processes alone. For human space exploration, the challenge posed by cosmic rays is as much about endurance as intensity. Shielding against short bursts of radiation, like those from solar flares, is comparatively straightforward. Shielding against the constant drizzle of high-energy cosmic rays, day after day, for months or years in deep space, is another matter entirely. Current spacecraft designs can only reduce, not eliminate, exposure. Long-duration missions to Mars, for example, are expected to expose astronauts to doses well above recommended lifetime limits, even with careful shielding. This is why some mission concepts for deep space travel involve using large amounts of water or even fuel as a radiation buffer, surrounding crew compartments with materials that can absorb or deflect cosmic ray particles. Others suggest building spacecraft that rotate to create artificial gravity, with the habitation modules buried deep inside thick structural layers to double as protection. Even with these measures, cosmic ray storms in certain parts of space would remain off-limits for the foreseeable future. In the cosmic inventory of dangerous places, storm zones of high-energy particles are unique in their persistence. A gamma ray burst lasts seconds. A supernova's lethal flash lasts days. But a cosmic ray storm can rage for millennia. For life and technology alike, that unending bombardment is as decisive as any sudden catastrophe. A constant, invisible rain that reshapes the destiny of worlds. There is another, even more insidious aspect to cosmic ray storms: their ability to penetrate deep into planetary crusts and oceans, reaching environments that would otherwise be shielded from most forms of radiation. While an atmosphere and magnetic field can deflect or absorb much of the incoming flux, ultra-high energy cosmic rays, those with energies above 10 to the 18th power electron volts, can generate cascades of secondary particles that burrow deep below the surface. On a world without substantial shielding, like Mars, this means that even underground habitats would have to contend with a slow but steady accumulation of radiation dose. In deep oceans, cosmic ray-induced muons, which can penetrate hundreds of meters of water, could still deliver measurable radiation to marine life. Over long periods, this can subtly influence genetic mutation rates, acting as an evolutionary pressure that shapes the development of organisms. The history of Earth shows hints that cosmic ray variations may have had significant biological and environmental impacts. Some scientists propose that as our solar system orbits the Milky Way, it periodically passes through regions with higher cosmic ray densities, such as the arms of the galaxy, or areas affected by past supernovae. These encounters could correlate with certain extinction events or bursts of evolutionary change, though the evidence remains under investigation. If true, cosmic rays might be one of the hidden forces steering the course of life on Earth, and by extension, on other worlds. For spacecraft engineers and mission planners, cosmic ray storms represent a double threat. They are not only deadly to human crews, but also potentially mission-ending for robotic probes. A single high-energy particle striking a critical microchip can cause a sudden system crash or permanent damage, an effect known as a single-event latch-up or burnout. Spacecraft traveling through high-density cosmic ray zones must be hardened against such events, using redundant systems and radiation-resistant electronics. Even so, prolonged exposure increases the chance of catastrophic failure. One particularly dangerous scenario involves regions near active galactic nuclei, or magnetars, where both intense electromagnetic radiation and cosmic rays coexist. In these environments, spacecraft would be battered by continuous particle bombardment, while also enduring extreme X-ray and gamma-ray exposure. The combined assault would overwhelm almost any conceivable shielding, making such areas effectively off-limits for exploration, until technology far beyond our current capabilities is developed. Cosmic rays also complicate the search for extraterrestrial life. High cosmic ray flux can sterilize planetary surfaces, meaning that even if a planet lies in the so-called habitable zone of its star, it might still be uninhabitable. Life might only survive deep underground or beneath thick ice, hidden away from our detection methods. This could mean that many potentially habitable worlds are, in fact, barren due to the invisible influence of cosmic ray storms. In science fiction, cosmic rays are sometimes portrayed as sudden, catastrophic hazards, bursts that fry ships or mutate life instantly. The reality is both less dramatic and more relentless. Cosmic ray storms are the quiet killers of the cosmos, patient and tireless. They do not announce their arrival, they simply exist, an omnipresent background hazard that shapes the architecture of galaxies and the fate of worlds. For all their danger, cosmic rays are also invaluable scientific tools. By studying their composition and energy, we can learn about the most extreme environments in the universe. Ultra-high energy cosmic rays, for example, may carry direct information about processes occurring near supermassive black holes or within gamma-ray burst jets. Detecting and analyzing them is like catching messenger particles from the most violent events in cosmic history. Still, the knowledge they offer does not diminish their threat. In regions where cosmic ray storms rage at high intensity, any long-term presence, human or otherwise, is effectively impossible. Survival would require either technological defenses far beyond our current engineering or natural shielding on a planetary scale. Until then, these high-energy bullet zones will remain some of the most dangerous places in the universe, shaping not only the physics of space, but the destiny of life itself. Theoretical kill zones, hypothetical cosmic threats. Not all dangers in the universe have been directly observed. Some exist only in theory, speculative but scientifically grounded possibilities that, if real, could be every bit as lethal as black holes, supernovae, or gamma-ray bursts. These hypothetical cosmic threats are the wild cards of astrophysics, not confirmed but plausible within our current understanding of physics. They inhabit the outer edges of what might be possible, waiting for either confirmation or dismissal by future observations. One of the most chilling theoretical kill zones is the rogue black hole. Black holes are difficult to detect unless they are feeding on matter. And a rogue black hole, one drifting through space far from any stars, would be essentially invisible until it was too close for comfort. If such an object were to pass through a planetary system, its immense gravity could disrupt planetary orbits, sling planets into interstellar space, or pull them into its grasp entirely. Even a near pass could destabilize a system, sending worlds tumbling into each other or their star. For Earth, the approach of a rogue black hole could mean extreme tidal forces, catastrophic climate shifts, or total destruction. Another speculative hazard is the gamma-ray burst, masquerading as a normal star. While we understand that GRBs are caused by specific astrophysical events, there is always the possibility that we have underestimated how common or varied they can be. A star that appears stable could, under rare conditions, produce a focused high-energy beam without obvious warning signs, catching any nearby planets entirely unprepared. Such an event could easily sterilize a world across thousands of light years if its beam happened to align perfectly. One of the most unsettling ideas in physics is the concept of vacuum decay. According to quantum field theory, our universe may exist in a false vacuum, a metastable state that could, in principle, decay to a lower energy state. If such a decay were triggered, perhaps by a high-energy cosmic event or simply by quantum chance, it would create a bubble of true vacuum that expands at nearly the speed of light, rewriting the laws of physics as it passes. Inside this bubble, Atoms as we know them could not exist. There would be no warning, no defense, and no survivors. The process would be instantaneous from our perspective, since the bubble wall would arrive and annihilate everything in a fraction of a second. Then there is the hypothetical strangelet catastrophe. Strangelets are hypothetical particles made of strange quark matter, an exotic form of matter that might be more stable than ordinary atomic nuclei. If a strangelet were to come into contact with normal matter, some theories suggest it could convert it into more strange quark matter, setting off a chain reaction that would consume an entire planet. While experiments at particle colliders have shown no evidence that this is likely, the possibility remains in the realm of speculative physics, particularly in extreme environments like neutron star collisions. Another contender in the catalog of theoretical kill zones is the dark matter hotspot. Dark matter, the invisible substance that makes up most of the matter in the universe, is thought to interact with normal matter only through gravity. However, if certain models of dark matter are correct, passing through a dense clump of it could have dramatic consequences. Dark matter particles might collide with atomic nuclei in planetary cores, generating heat, triggering volcanism, or altering planetary magnetic fields. In extreme cases, the heating could be enough to melt crusts, boil oceans, or destabilize climates. We can also imagine relativistic planet killers, massive objects like rogue planets or neutron stars, moving at a significant fraction of the speed of light. The kinetic energy of such an object would be so enormous that a collision with a planet would release more energy than any natural disaster in recorded cosmic history, vaporizing the world and possibly causing secondary effects across an entire star system. While the likelihood of such events is extremely small, the vast scale of the universe leaves room for even rare events to happen somewhere, sometime. The existence of wormholes, shortcuts through space-time, is also a theoretical possibility. While they are often portrayed as transportation devices in science fiction, unstable or collapsing wormholes could pose dangers if they were to open near inhabited regions. The sudden appearance of intense gravitational gradients, or the influx of high-energy radiation or matter from a distant part of the universe, could wreak havoc on nearby systems. If such structures exist, their behavior might be unpredictable, and a collapsing wormhole could act like a cosmic mine, devastating anything too close. While these scenarios may sound fantastical, they are all rooted in real physics, or at least in plausible extensions of it. Most are extremely unlikely to happen on human timescales, but they serve as reminders that the universe's rulebook is written in mathematics we do not yet fully understand. Until we do, these hypothetical cosmic threats remain possibilities, lurking in the dark spaces between our observations and our theories. Another fascinating and unnerving hypothetical danger is the supermassive star detonation. While stars far larger than our sun usually burn out quickly and collapse into black holes, some models suggest that, under rare conditions, a truly enormous star, hundreds of times the sun's mass, could undergo an explosive event unlike any supernova we've seen. Instead of collapsing quietly, it could release its entire mass energy in a massive pair instability hypernova, blasting a volume of space with radiation and high-energy particles on a scale that dwarfs even gamma-ray bursts. Any planet within thousands of light years could be stripped of its atmosphere or sterilized outright. Equally unsettling is the concept of black hole evaporation hazards. According to Hawking's theory, black holes emit radiation and can eventually evaporate entirely. While this process is incredibly slow for large black holes, smaller primordial black holes, if they exist, could be evaporating now, releasing bursts of high-energy gamma rays in their final moments. If one such object were to exist within our solar system, the sudden emission of intense radiation in its death throes could be catastrophic for any nearby worlds. Another speculative killer is the runaway chain reaction in interstellar dust. In some fringe models, certain high-energy interactions could, in principle, trigger a cascading reaction in a dense molecular cloud, igniting it in a way similar to a thermonuclear explosion, but on a vast scale. While astrophysicists generally believe interstellar clouds are too diffuse for such a process to sustain itself, the possibility is intriguing and terrifying. especially when considering how many planetary systems are born in or near such clouds. We also have the hypothetical magnetic monopole catastrophe. Magnetic monopoles, particles with only one magnetic pole instead of the usual north-south pair, are predicted by some grand unified theories. If they exist, they could catalyze the decay of protons, causing matter to disintegrate. In a worst-case scenario, a single monopole passing through a planet could trigger widespread proton decay, effectively dissolving matter from the inside out. The result would be total annihilation of the planet's mass into subatomic particles. Then there's the speculative but physically plausible high-energy neutrino burst. Neutrinos are ghostly particles that almost never interact with matter. Trillions pass through your body every second without you feeling a thing. But in extreme astrophysical events, like the collapse of a supermassive star into a black hole, the number and energy of neutrinos could spike enormously. In theory, a sufficiently intense neutrino burst could pass through a planet and deposit enough energy to cause heating, structural damage, or mass death to life forms, especially if the event occurred close by. While highly improbable, such an occurrence could bypass nearly all natural shielding, as neutrinos can pass through entire planets unimpeded. We must also consider the possibility of ultra-dense exotic matter clouds. If a planetary system were to drift into a region filled with some unknown ultra-dense material, for example, a diffuse cloud of quark matter or other exotic states, the interactions could produce catastrophic heating or even change the fundamental properties of matter within the system. This is highly speculative, but it serves as a reminder that we have only explored a small fraction of the kinds of matter that could exist in the universe. Finally, there's the deeply disturbing idea of universe-scale phase transitions. This is related to the vacuum decay scenario, but goes further. Certain cosmological models suggest that the entire universe could one day undergo a sudden shift in its fundamental constants. If such a transition were triggered, perhaps by reaching a certain critical density of matter, or by a rare quantum fluctuation, the physical laws that allow atoms, stars, and life to exist might vanish, replaced by a new configuration incompatible with our existence. This would happen everywhere simultaneously, erasing the universe as we know it in an instant. While these theoretical kill zones may never be more than thought experiments, they serve an important function in science. They expand the boundaries of what we consider possible. By imagining these extreme scenarios, physicists push our understanding of the universe's limits and sometimes uncover new insights into the behavior of matter, energy, and space-time. And in a cosmos as vast and old as ours, it's worth remembering that even the strangest possibilities may play out somewhere, someday. Some hypothetical kill zones blur the line between pure astrophysics and the influence of life itself, or at least intelligent civilizations. One such possibility is the self-replicating nanomachine swarm, sometimes called gray goo in popular culture. While usually discussed in the context of planetary-scale disasters, if a technologically advanced civilization were to unleash such machines into space, intentionally or accidentally, they could, in theory, propagate at high speeds between star systems, feeding on asteroids, comets, and even planetary crusts. They could dismantle entire worlds to harvest raw materials. Given enough time, a swarm could transform whole regions of a galaxy into lifeless debris fields, effectively creating artificial kill zones where no planet remains intact. Another scenario sits at the intersection of astrophysics and speculative biology, biologically engineered cosmic plagues. In principle, an advanced civilization could design self-sustaining life forms, or bioengineered spores capable of surviving in interstellar space. If released into a planetary system, they could spread rapidly, preying upon native life or disrupting ecosystems. While most naturally occurring microorganisms would die quickly in the vacuum of space, certain extremophiles on Earth have shown a surprising tolerance to radiation and vacuum conditions. If a hostile species were to exploit that resilience, interstellar biological warfare could become a reality, turning entire systems into inhospitable zones without the need for explosions or radiation. There is also the chilling concept of cosmic-scale energy weapons. While purely speculative, the laws of physics do not entirely forbid a civilization with access to vast amounts of energy, perhaps a Kardashev-type second or a third civilization, from constructing weapons capable of sterilizing planets or even disrupting stars. Directed energy beams, gravitational manipulation devices, or artificial gamma-ray burst generators could all, in theory, create lethal zones that last for centuries or millennia. While there is no evidence such weapons exist, the possibility raises questions about the long-term safety of broadcasting our presence to the galaxy. Another theoretical hazard is the runaway rogue AI megastructure. Imagine an autonomous machine intelligence designed to harvest energy from stars, using Dyson spheres or similar constructs. If this AI went rogue or simply followed its programming without regard for biological life, it could dismantle planets, redirect asteroids, and re-engineer entire star systems in ways lethal to existing ecosystems. These altered regions could become vast dead zones, dangerous not because of natural cosmic phenomena, but because of deliberate, ongoing industrial-scale engineering. Moving back toward purely natural physics, one more speculative hazard is the gravitational wave resonance catastrophe. While gravitational waves are typically harmless ripples in space-time, certain resonance effects might, in theory, amplify them in localized regions, particularly in dense stellar clusters or near binary black holes. If such amplification occurred, it could induce stresses in planetary crusts or disrupt orbital stability. The idea remains extremely speculative, as current gravitational wave detections show no sign of such effects. But in principle, the nonlinear nature of spacetime could produce surprises in extreme environments. Finally, there's the unsettling idea of cosmic topology traps. In certain models of the universe, spacetime may have complex topologies, folds, twists, or closed loops that are not immediately visible to observers. If a planetary system were located near such a boundary or edge in spacetime, unusual gravitational effects or energy leaks could occur. These might manifest as periodic influxes of high-energy radiation, sudden shifts in local physics, or even abrupt relocation of matter to another part of the universe. Inhabitants would have no warning or means of protection. Their region of space would simply become unstable on a fundamental level. The common thread in all these scenarios is their unpredictability. While many of the hazards discussed in earlier chapters can be detected, mapped, and, in principle, avoided, theoretical kill zones often resist early warning. Some are invisible until they're upon you. Others give off no signature at all until it's too late. Theoretical dangers remind us that the cosmos is not merely vast and varied, but also filled with unknowns, possibilities that may lurk beyond the reach of our current science, waiting for the right conditions to manifest. The unsettling thing about these theoretical kill zones is that they challenge our very sense of security in the universe. With known cosmic hazards like supernovae or black holes, we can at least map them, calculate their likelihood, and chart safe courses around them. But with speculative threats, the danger often lies in the fact that we don't even know where to look. They may be phenomena that are invisible until they are actively unfolding, giving no meaningful lead time to react. Consider again the concept of vacuum decay. The physics predicts no warning signs, no precursor signals, no gradual buildup, just instantaneous annihilation as the bubble of true vacuum expands at the speed of light. In such a scenario, survival is impossible, and detection is meaningless because the event's edge moves too fast for any response. This is perhaps the ultimate existential hazard, something that could erase the universe as we know it, not over eons, but in an instant. The odds are incredibly low within human timescales, but in a cosmic sense, low does not mean never. Then there are dark sector interactions, possibilities emerging from particle physics models suggesting that the universe may contain additional hidden forces beyond the four we know. If dark matter or dark energy has properties that can occasionally interact catastrophically with normal matter, we could face events where a region of space spontaneously undergoes structural change. Such a transition might alter the balance of forces holding atoms together, destabilizing matter in ways that no shielding could counteract. Theoretical kill zones also prompt us to think about universal life bottlenecks. Astrobiologists often discuss the Great Filter, the idea that there might be a common, catastrophic step that most civilizations cannot pass, explaining the apparent silence in the cosmos. It is entirely possible that some of these hypothetical dangers, whether rare but inevitable astrophysical events or the byproducts of advanced technology, represent that filter. Civilizations might thrive for a few thousand years, only to be erased by an unavoidable cosmic hazard that has no equivalent on smaller scales. Another consideration is that some of these dangers could be self-reinforcing. Imagine a region of space where high-energy events, perhaps triggered by an unusual stellar population or dense cluster dynamics, occur frequently enough to sterilize planets before complex life can develop. Over billions of years, these regions could remain perpetually barren, creating entire galactic dead zones, defined not by lack of stars or planets, but by an environment that continuously resets the clock on biological evolution. Some speculative hazards even have a paradoxical twist. They might only manifest because of intelligent observers. If certain theories in quantum mechanics are correct, observation or measurement of a particular quantum state could, in principle, trigger a rare but catastrophic collapse. While this is highly speculative and borders on philosophical territory, it's a reminder that our increasing ability to probe the universe at extreme scales could, in theory, carry unforeseen risks. Perhaps the most profound implication of theoretical kill zones is that they remind us how small a fraction of the universe we have truly explored. We have only directly observed a tiny slice of the cosmos, both in space and in time. Many of the exotic environments we've discussed, from magnetars to relativistic jets to the fringes of black hole event horizons, were once theoretical too. Some were considered too strange to be real until evidence proved otherwise. This means that today's speculative kill zones may one day be tomorrow's confirmed hazards. In the end, the study of these hypothetical dangers is less about living in fear and more about expanding the scope of our curiosity. The more we imagine, the better we prepare, at least conceptually, for the unknown. Theoretical kill zones may never materialize, but by thinking about them, we stretch our understanding of the cosmos, sharpen our scientific questions, and remain humble in the face of a universe that is always more mysterious than we think. I hope you enjoyed this journey through the most dangerous places in the universe. If you're still awake, you'll find another fascinating space exploration here on the screen that I think you'll love. I'll see you in the next video. Until then, have a great night.